The beginning of this course includes a big review of some very important topics in chemistry, such as acids and bases. Hopefully you remember some of the basics of acids and bases, but we will review them here in case you need a refresher. There are three different definitions of acids and bases, but we will mainly focus on the Bronsted-Lowry definitions. Keep in mind that when we are talking about acids and bases here, we are always talking about aqueous solutions. An acid is a proton donor, meaning it gives up H+ ions. Acidic solutions have a pH of less than 7. Because an acid loses a proton, it gets oxidized. A strong acid is an acid which deprotonates completely, meaning it exists as ions rather than as a neutral compound. For example, HCl is a strong acid that dissociates completely into H+ and Cl- ions, rather than existing as HCl. A weak acid is an acid that does not deprotonate completely, meaning that only a small amount of it is ionized and it exists mostly as a neutral compound. HF is a weak acid, so it exists mostly as HF rather than H+ and F-. In order to tell if an acid is strong or weak, you can look at a table of Ka values, which we'll talk about more in a few minutes. When an acid loses its proton, the anion that is left is known as the conjugate base. While the Bronsted-Lowry definition of an acid is something that donates protons, a base accepts protons. The Lewis definition of a base is a substance that donates hydroxide ions. Basic solutions have pHs greater than 7. Because a base accepts protons, it gets reduced. A strong base accepts protons readily, or alternatively, it donates hydroxide ions readily. A weak base does not accept protons readily, nor does it donate hydroxide ions readily. After a base gains a proton, the resulting substance is known as the conjugate acid. Just from looking at the way this equation is written, we can tell that HCl is a strong acid. The fact that a single one-directional arrow exists tells us that the reaction proceeds in only one direction and that all of the HCl gets broken down into H+ and Cl-. However, it is important to note that this reaction is not complete. It is not the case that the HCl spontaneously breaks down into H+ and Cl-. Rather, there is another substance that causes that dissociation to happen. To write the reaction more completely, water rips the protein away from the HCl, leaving a hydronium ion, H3O+, and a chloride ion, Cl-. Looking carefully at this equation, we can see that water gains a proton and hydrochloric acid loses one. As a result, HCl is the acid and water is the base. Once HCl loses its proton, it becomes the conjugate base. The water that has taken the proton from HCl becomes H3O+, the conjugate acid. We know that HCl is a strong acid. When it loses its proton to become Cl-, the Cl- is a weak conjugate base. The reason that the acid is strong and the conjugate base is weak is because if the acid readily dissociates, the conjugate base will not readily take on the proton that has just been lost. Let's look at the example of the dissociation of nitrous acid. We can tell that nitrous acid is a weak acid because of the double arrow, indicating that the reaction occurs in both directions. Again, however, this is not the complete picture. What is actually happening is that a water molecule is ripping the proton away from the nitrous acid. Since the nitrous acid is losing the proton and the water molecule is gaining it, we know that HNO2 is the acid and the water is the base. Once HNO2 loses the proton, the anion that results is NO2- and is known as the conjugate base. The water that has taken the proton from the HNO2 is the conjugate acid. In this case, HNO2 is a weak acid. Therefore, NO2- is a strong conjugate base, as it will readily accept protons to become HNO2. Knowing the pH of a solution gives us an idea of the amount of hydrogen ions in the solution. In order to calculate pH, take the negative log of the concentration of hydrogen ions in the solution. Similarly, to find the pOH, take the negative log of the concentration of hydroxide ions. A higher concentration of hydrogen ions means a more acidic solution or a solution with a lower pH. The pH range is 0 to 14, with acids having a pH from 0 to 7 and bases having a pH from 7 to 14. Hopefully you remember the idea of equilibrium constants from chemistry. An equilibrium constant tells you the ratio of the concentrations of products to reactants in a given solution. Imagine you had the following equation. AA plus BB yields CC plus DD. The equilibrium constant, or the KEQ, is written as the concentrations of the products divided by the concentrations of the reactants. In this case, KEQ is the concentration of C raised to the C power times the concentration of D raised to the D power divided by the concentration of A raised to the A power times the concentration of B raised to the B power. Remember that the concentrations of pure solids and liquids are constant, so the only states that get included in the equilibrium expressions are aqueous solutions and gases. We can look at the dissociation of water and write an equilibrium expression for that reaction as well. Notice that the H2O on the left-hand side of the equation is much larger than the ions on the right-hand side of the equation. This is because water is a very weak acid, so most of it will exist in its non-ionized form. Instead of calling the equilibrium expression KEQ, we will call it KW, indicating that it is an equilibrium expression for water. Water ionizes to H+ and OH-. We can write the equilibrium expression, or the KW, as the concentration of H+ times the concentration of OH-. Remember that the water doesn't get included in the equilibrium expression because it is a pure liquid. It turns out that the K value for this reaction is 1.0 times 10 to the minus 14th, a very small number. This means that water exists primarily as H2O rather than as its ions H+ and OH-. Taking the square root of 1.0 times 10 to the minus 14th allows us to determine the concentration of H+, which is equal to the concentration of OH-, which is equal to 1.0 times 10 to the minus 7th molar. Taking the negative log of this number shows us that the pH of water is 7, which makes sense as we know that water is a neutral substance. We can also calculate the pOH by taking the negative log of the concentration of OH-. The pOH would be 7 as well. At this point, we need to note another important equation when talking about acids and bases. The pH plus the pOH always equals 14. As was mentioned earlier, a weak acid is an acid that doesn't deprotonate fully, so that most of it is left in its non-ionized state. However, a small amount does break down into ions, giving us the following equilibrium. We can write an equilibrium expression known as a Ka with the A for acid, for the dissociation of this weak acid. Because the acid is weak and exists mainly in the non-ionized form, we would expect the concentration of products to be very small relative to the concentration of reactants, therefore yielding a small value for the Ka. Keeping in mind that K equals the concentration of products over reactants, in this case, Ka equals the concentration of H plus times the concentration of A minus divided by the concentration of HA. Similarly to the idea of pH, the pKa is the negative log of the Ka. Stronger acids have larger Ka values than weaker acids because they dissociate more completely, causing the concentration of the products relative to the reactants to be greater. As a result, stronger acids have lower pKs than weaker acids. In order to write the equilibrium expression for the dissociation of acetic acid, we first need to write the dissociation itself. Acetic acid dissociates into H plus and CH3COO-. The Ka will be the concentration of the products, H plus and CH3COO-, divided by the concentration of the reactant, CH3COOH. If the Ka for acetic acid is 1.74 times 10 to the minus fifth, the pKa can be calculated by taking the negative log of the Ka. The pKa equals 4.76.